Hi, hello, welcome you all for today's classes that is Introduction to Heat Transfer. Today we are going to start the heat transfer syllabus. Okay, so first we should know what and why heat transfer is needed. Being a mechanical engineer, so why we need to study the heat transfer subject. So first we should know those things, and also we also discussed today that some words, that is the basics words, that is heat, thermodynamics and heat transfer, and what are the mode of heat transfer, why we need to study this heat transfer. Okay, so first heat. What is the heat? It is the form of energy. Heat is the form of energy that can be transferred, that can be transferred from one system to the another system as a result of temperature differences. So you can transfer the heat from one system to the another system. So it is as the result of temperature differences. That means what? If there is a temperature differences between the two systems, two substances, then there is a heat is transferred from one system to the another system. First of all, this heat is the form of energy. Heat is the form of energy. And one thing we should know that temperature is not a change. Temperature is not a change. Just the heat is changed. Or sorry, temperature is not transferred. Just heat is transferred from one substance to the another substances. Okay, so that heat is the form of energy that can be transferred from one system to the another system as a result of temperature differences. Okay, and next one is the thermodynamics. It is concerned with amount of heat transfer. It is concerned with amount of heat transfer as a system undergoes a process. It is, it is concerned with the amount of heat transfer as a system undergoes a process. So from one equilibrium state to the another equilibrium state. One equilibrium state to the another. Okay. So it is concerned with the amount of heat transfer as a system undergoes a process from one equilibrium state to the another system, another state. So that means what? So how much amount of heat is transferred? As you know, the heat is a form of energy and it can be transferred from one system to the another system. So in the thermodynamics, we are concerned about the how much amount of heat is transferred. How much amount of heat is transferred when a system undergoes a processes. When a system undergoes a processes, the amount of heat is transferred. So that thermodynamics term concerned with how much amount of heat is transferred when the system is undergoes a processes and from one equilibrium state to the another. So that the term thermo is nothing but the heat, dynamics is nothing but the motion. So that heat, the motion of heat, motion of heat. So that thermodynamics is nothing but what? Motion of heat. So here thermodynamics is concerned with how much amount of heat is transferred when the system undergoes a processes and from equilibrium state to the another equilibrium state to the another. Okay. So now heat transfer. Heat transfer. The term heat transfer deals with the determination of the rates of such energy. Rates of such energy. Such energy is what? Heat energy. It, it deals with the determination of the rates of such energy. Such energy, but heat energy transfer as well as variation of temperature. Variation of temperature. The heat transfer deals with the determination of the rate, at what rate the heat is transferred. At what rate the heat is transferred, and also variation of the temperature. Variation of the temperature. So heat transfer is deals with determination of calculation of the rate of heat energy transfer and also the variation of the temperature. So it includes both the determination in the heat transfer. Okay. Next, the transfer of energy as a heat is always from higher temperature medium to the lower temperature one. Okay. So it is nothing but what the heat is always transferred from the higher temperature medium to the lower temperature one. That means heat is transferred due to the temperature differences between the substances, between the part of the substances. Okay. Due to the temperature differences only the heat is transferred. But at what temperature to what temperature? At higher temperature medium to the lower temperature. The heat can be flow from higher temperature medium to the lower temperature 1. Okay, it is always flow from the higher temperature to the lower temperature region. Okay, next, heat transfer stops when two medium reaches the same temperature. The heat transfer stops when the two medium reaches the same temperature. As you know, heat transfer is due to the temperature differences, okay, between the substances. If those substances will reaches the same temperature, those substances will reaches the same temperature, then the heat transfer stops. Heat transfer stops. Okay, if the two substances reaches the equilibrium temperature or the same temperature, then the heat transfer stops within those two substances. Okay, heat can be transferred in three different modes. Okay, we know that heat is transferred between one substance to the another substance. Okay, so it required some modes to transfer the heat. It requires some modes. Okay, so what are those modes? There are three different modes to transfer the heat from one substance to the another substances. What are those? Conduction, convection, and radiation. These three are the three mode of heat transfer. Three mode of heat transfer. Okay, so through these modes only the heat is transferred between the substances or between the part of the substances. Okay, so now these are the some basics terms or the definitions which you have to study in our heat transfer subject. Okay, what are those? Heat, thermodynamics, heat transfer, and the heat is transferred higher temperature region to the lower temperature region, and the heat transfer stops when when it stops, two medium reaches the same temperature, and heat can be transferred in three different modes. What are those modes? Conduction, convection, and radiation. Okay. Now, these two words, another two words are very important to study is the heat transfer. What are those? Steady state and the unsteady state. What is the steady state? Temperature varies with the position. Temperature varies with the position, but it does not varies with the time. Okay. If the temperature of any components or any substances, it will varies with respect to the position, but it does not varies with respect to the time. If the time varies, the temperature remains constant, or if it is the substance's temperature varies with different positions with different directions. So such type of state is called as a steady state. Steady state. The temperature varies with the position, but it does not vary with the time. But it does not varies with the time. Okay. So that is given by T is equal to function of xyz. So this xyz is representing the position of the components or any substances. Okay, if in x position, y position, z position, there is a different temperature that we indicates the varies. The temperature varies with the positions. Suppose if you are having one components or the substances, its temperature is different in x directions, y positions, and z positions. X position, y position, that we indicates the varies with the position, but it does not vary with the time. Suppose if you are consider one substances which is of having 100 degrees Celsius, okay, So if you are checking at 100 degrees Celsius at one time, and later if you check that the same substances or components after 1 hour or half an hour, if it is remains constant, or you can check that substance temperature at any time it remains shows the 100 degrees Celsius only, then the components or the substances is called as a steady state substances or steady state components. Okay, so that's why in the steady state the temperature of the components or the substance is a function of only the positions, that is x, y, z position. Okay, so next here unsteady state. Unsteady state. Temperature vary with the time and the position. In the unsteady state, so the temperature is the function of both x, y, z and also the time tau. And also the time tau. Here the components of the substances temperature is varies with respect to the time as well as the positions, that x, y, z positions. That type of substances or components is called as a unsteady state. Unsteady state. Okay, we should know these two differences. Steady state is nothing but what? The temperature of the components or the substantial varies only with respect to the position, not with the time. But in the unsteady state, temperature of the substances or the components will vary with respect to time as well as the position. That will be given here T is equal to function of x, y, z and tau. Okay. So this is about the part and why the heat transfer. Okay. In the next application areas of heat transfer. Application areas of heat transfer. So here you can apply this heat transfer concept. Here you can apply this heat transfer content. So this application can be studied with respect to the different field of engineering. Field of engineering. So first you can take the mechanical engineering. Here you can use this in mechanical engineering in the boiler, okay, and heat exchangers, turbine system, IC engine, and etc. So you can use this heat transfer concept in the boiler, heat exchanger, turbine system, IC engine, and so many things. So many applications in the mechanical engineering. So we can in the boiler, what happens that heat is transferred from steam to the water, steam to the sorry gases to the water, boiled gases to the water. So like this, the heat is transferred in these applications. In the metallurgical engineering, the furnaces heat treatment of the components. In the furnaces and heat treatment of the components. In the metallurgical engineering field, you can use this heat transfer concept in the furnaces and heat treatment of components. Heat treatment of components. Okay. Next one is in the electrical engineering, where you can use this cooling system for the electric motors, generators, and transformers. Cooling systems for the electric motor, generator, transformer. Okay, and in the chemical engineering, the process equipments used in the refiners, chemical plants. In the chemical engineering, you can use the process equipments used in refineries and chemical plants. You can use the chemical plants. Okay, so in the nuclear engineering, the removal of heat generated by the nuclear fusion. So if there is a fusion process, a large amount of heat is produced, so we can remove some amount of heat. So by using the liquid metal coolants, design of nuclear fuel rods against possible burnout. So you can use this nuclear in the heat transfer concept in the nuclear energy to remove of heat from the fusion using liquid metal. Using this liquid metal, you can uh, remove the heat generated by the nuclear fusion. Okay. Next one is the aerospace engineering and space technology. So here in this field, you can use this heat transfer in design of aircraft system and components. Design of aircraft system and components, rockets, etc. Okay, design of aircraft systems and components and rockets, etc. Next one is the cryogenic engineering. In the cryogenic engineering, production, storage, transportation, and utilization of cryogenic liquids at very low temperature, ranging from 100 Kelvin to the 4 Kelvin or even lower. So, in the cryogenic engineering, you can use this heat transfer concept in the production, storage, transportation, and utilization of the cryogenic liquids. So, these liquids will maintain at a very low temperature that ranging from 100 Kelvin to the 4 Kelvin or even lower one, even lower. So these are some uh, application areas of heat transfer. Okay. The next one is the conduction. Now we can study the mode of heat transfer. So there are basically three mode of heat transfers are there. What are those? Conduction, convection, and radiation. Okay. First we go through one by one. So here conduction. First, conduction. The transfer of heat from one part of a substance to the another part of the same substance, or from one substance to the another in physical contact with it, okay, without any appreciable displacement of molecules forming the substance. Okay, displacement of molecules forming the substance. That means what? Here, in the conduction mode of heat transfer, the heat transfer from one part of the substance to the another part of the same substance. Okay, so if you are considered this is one substance, the heat is transferred from this side to this side. If T1 is greater than the temperature at this side is greater than T2, then what happens? The heat is transferred from this part of the substance to this part of the substances. That is what here one part of the substance to the another part of the same substance. If you are considered this is one substance, one part of the substance to the another part of the same substances. Or, or sometimes what happens? The heat is transferred between two different substances when they are in contact to each other. If you are considered this is one substances, and you can take one another substances which is come in contact with the this substances, okay, so that times what happens, the temperature of this substance is more than the another substances. So that case what happens, the heat is transferred between this substance to the another substance which is contacting with this substance. Okay, so that is the what? Conduction. Conduction is nothing but what? The heat is transferred between the two substances when they are in come in contact with each other, or the heat is transferred from one part of the substance to the another part of the same substance. Okay. Next, in gases and liquids, in gases and liquids, conduction is due to the collisions and diffusion of the molecules during their random motion. Okay. So in the gases and liquids, so what happens to this conduction is due to the collision and diffusion of the molecules during their random motion. So heat takes place in the gases and liquids. So this conduction it is a solid body. It is a solid body. The conduction takes place between these two parts. But in the gases and liquids, the conduction is due to the collision and diffusion. Collision and diffusion of the molecules during their random motions, the conduction of heat transfer takes place. Okay. In solids, it is due to the combination of vibration of molecules in the lattice and the energy transferred by the free electrons. So, in the gases and liquids, conduction is due to the collision and diffusion of the molecules which are present in the gases and liquids. Okay, the molecules are present in the gases and liquids. The conduction is due to the collision and diffusion. But in the solids, it is due to the combination of vibration of the molecules. Combination of vibration of the molecules in lattice. In lattice, and the energy transferred by the free electron. Due to these two, reasons, in the solids, the conduction of heat transfer takes place. Conduction of heat transfer takes place. Okay, in the solids, due to what? The combination of vibration and the free electron. In the gases and liquids, the conduction is due to the collision and diffusion. Collision and diffusion. Okay. Next, the rate of heat conduction through the plane layer is proportional to the temperature differences across the layer and the heat transfer area, but it is inversely proportional to the thickness of the layer. Okay. So this we will study it by while studying the laws, governing laws of the conduction. Okay. The rate of heat conduction through the plane layer is proportional to the temperature differences across the layer and the heat transfer area, but it is inversely proportional to the thickness of the layer. So you can observe here one heat conduction through a large plane wall of thickness delta x and area. Okay, so what happens here, it states that the rate of heat conduction, that is rate of heat conduction, is directly proportional to the area and the temperature difference, area and temperature differences, and inversely proportional to the thickness of the layer delta x. Delta x. That is, that means if you are here in this figure, you can take that q dot is the heat transfer. Q dot, it indicates the heat transfer. This is directly proportional to the temperature differences. It is T1 minus T2 into area, into area. That is, you can say that q dot is directly proportional to the delta t into a, delta t into a, and this q dot is inversely proportional to the thickness of this wall. That what the statement is given here. The rate of heat transfer conduction through the plane wall is proportional to the directly proportional to the temperature differences and the area, inversely proportional to the thickness, inversely proportional to the thickness. Okay, so this is the conduction mode of heat transfer. Conduction is nothing but what? The heat is transferred from one part of the substance to the another part of the same substances, or one substance to the another substances, when both those substances are coming in contact with each other. Okay. So in the gases and liquids, the conduction mode of heat transfer takes place due to the collision and diffusion of the molecules, and in the solids, it takes place due to the combination of vibrations and free electrons of the molecules. Vibration and free electrons of the molecules. Okay. So this is the conduction. Next one is the Fourier law of heat conduction. All these three modes of heat transfer, that is conduction, convection, and radiation, will have some one governing laws with respect to that governing laws. So what are those? First, Fourier law of heat conduction. The conduction mode of heat transfer will have the governing laws of Fourier laws of heat conduction. Fourier's laws of heat conduction. What it states that here, the empirical law of conduction based on the experimental result is named after the French physicist Joseph Fourier. So here he is the Joseph Fourier. After conducting the experiment, he got some results. So based on that results, he came to uh, state. He came to give the statement of laws on the conduction. Okay, so that French physicist Joseph Fourier. What is the statement of this Fourier law of heat conduction here? The laws state that the rate of heat flow by the conduction in any medium in any direction is proportional to the area normal to the direction of heat flow, and also proportional to the temperature gradient in that direction. So rate of heat conduction. So you can get here, rate of heat conduction is directly proportional to the area and the temperature differences, and inversely proportional to the thickness. So in the previous slides, here he has given some statements. The rate of heat conduction through the plane layer is proportional to the temperature differences across the layer and the heat transfer area, but it is inversely proportional to the thickness of the layer. So this statement is given by the Fourier law of heat conduction. That is given here. The last states that the rate of heat flow by the conduction in any medium in any direction is proportional to the area normal to the direction of heat flow, and also proportional to the temperature gradient, or you can say the temperature differences in that direction. So that is rate of heat conduction is directly proportional to the area into temperature differences and inversely proportional to the thickness. So in the mathematical, you can give that Q conduction is equal to Ka T1 minus T2 divided by delta X. So which is equal to minus Ka delta T by delta X. Measure in the its unit is watt. Its unit is watt. When x equal to 0, Q conduction is equal to what? Minus Ka dt by Q. When x tends to 0, Q conduction is equal to minus Ka dt by dt. So this equation gives us the Fourier law of heat conduction. Fourier law of heat conduction. If you remember this equations, and this is very important equations in the conduction. If you remember this equation, you can easily give the statement of this Fourier law of heat conduction. See here, the rate of heat flow, that is Q conduction, is directly proportional to the area uh, area normal to the direction of heat flow, that is normal to the direction of heat flow, in which direction heat is flowing. So that is the area normal to that directions, and the temperature differences, that is the delta T, or you can say that dT, temperature differences, and inversely proportional to the thickness. You can add up this statement with the thickness, or you can left it. So you can write that the rate of heat flow is directly proportional to the area normal to the direction of heat flow, and also proportional to the temperature gradient in that directions, or temperature differences in that directions. Okay, so you can state that statement. That is the statement of Fourier law of heat conduction. So here, see, in the copper, K is the thermal conductivity, where K is equal to what? Thermal conductivity. Okay, uh, 30 degrees Celsius is there, here the 20 degrees Celsius is there, and the heat is transferred from this 30 degree to the 20 degrees Celsius, and the thickness of this is 1 meter, that is what? Delta X here, and Q is equal to 4010. If you substitute all these values, that is T1 minus T2 into area, if you find out this area by using this thickness, okay, and if you put all the values, you will get the Q is equal to 4010 watt per meter, watt per meter cube. So okay, here if you are considered the second example, okay, so this is for the silicon and this is for the copper, and the K value for both material is different here. It is K value is 401 per watt per meter degree Celsius. Here for silicon K is equal to 148 watt per meter degree Celsius. Okay, so in this what we should remember, the statement of the Fourier law is here: Q dot conduction is directly proportional to the area into delta T divided by delta X. That much you have to remember. Eh? And while conducting this experiment and while giving this statement, there are some assumptions which we have made. So those are: the heat flow is unidirectional. The heat is always flowing from the one direction only, that is from this side to this side, left side to the right side, or we can take that right side to the left side. Only we can take that unidirectional heat flow. Okay. Next is conduction is taking place in steady state. Conduction is taking place in steady state. What is the meaning of steady state here? Steady state is nothing but what? Temperature of the substances will not change with respect to the time, it changes only the position. Okay, that uh, here this substance we can consider it is a steady state substances or component. Okay, next, no internal heat generation. So within this substances or component, there is no heat generation takes place, there is no heat generation takes place. Okay, next, material is homogeneous and isentropic. Material is made up of only one material, only one material, that is homogeneous and isentropic material, and there is no internal heat generation, there is no heat generation content within the element, and the temperature gradient is constant and temperature profile is linear. Temperature gradient is constant, that is temperature difference is constant and hence the temperature profile is linear. So these assumptions are very very important while deriving these equations. By conducting the experiment, he made some assumptions to get this statement. These are the five assumptions. Okay. So next one is in the conduction only you can take the thermal conductivity. Thermal conductivity that K, that is represented with the K. So in the previous equations we are having that K value here. K A delta, if you remove this proportionality sign, then this K will added. So that is what thermal conductivity. So what is this thermal conductivity? A measure of ability of a material to conduct the heat. It is a measure of ability of a material to conduct the heat. That means what? Capability of a material to conduct the heat or to allow the heat to flow in that material. That is what ability of a material to conduct the heat. To conduct the heat. That means the heat is flowing from one point to the another point. So that ability to conduct the heat, that amount of heat is flowing. Okay. So that is something about what thermal conductivity. If the material will having the more thermal conductivity or the value of K is more, so that will gives us the more heat transfer, more heat transfer rate. Okay. If the material having the higher thermal conductivity value will gives us the more rate of heat transfer, more rate of heat transfer. Okay. If the material will having the lesser amount of thermal conductivity, that the lesser value of thermal conductivity value K, so the material will give us the low rate of heat conduction, low rate of heat flow, low rate of heat. That is the conductivity, a measure of ability of a material to conduct the heat. That is denoted by the K. Next, temperature gradient dT by dx. So this dT by dx entire term is called as a temperature gradient or rate of heat flow, rate of temperature. The slope of temperature curve on Tx diagram. It is the slope of temperature curve on Tx diagram. So that will give us the temperature gradient, that is dT by dx. Okay. Next, heat is conducted in the direction of decreasing temperature, and the temperature gradient becomes negative when temperature decreases with increasing x. Okay. So heat is conducted in the direction of decreasing temperature. So heat is conducted in the direction of decreasing temperature, and the temperature gradient becomes negative, so that this dt by dx becomes negative when the temperature decreases with increasing x. If the thickness of the material is increases, the thickness of the material is increasing, then the temperature gradient, when that is nothing but temperature differences, becomes decreases. It becomes get a negative value. It becomes get a negative value. If thickness is increases, the thickness means that is dx, this temperature differences becomes negative. That's why we can use that negative sign here, minus Ka dt by T. This minus indicating that if the thickness of this material is increases, the temperature difference between the substances is decreases, and it becomes tends to the negative. That's why we can use this negative sign. Okay. So that was here. The negative sign in the equation ensures that the heat transfer in the positive x direction is positive one. If the negative sign is indicating that heat is flowing from the higher temperature region to the lower temperature region, that will use the negative sign. Okay. So in heat conduction analysis, A represents the area normal to the direction of heat transfer. A is represents the area normal to the direction of heat transfer. Area, that is how this A is equal to W into H. So this is the W height into width. So this will give us the area normal to the direction of heat flow. Normal to the direction of heat flow. Okay. Next, the rate of heat conduction through the solid is directly proportional to its thermal conductivity. The rate of heat conduction through a solid is directly proportional to its thermal conductivity. That here the rate of heat conduction is directly proportional to the thermal conductivity. Thermal conductivity. These two are get directly proportional to each other. That will use it here. Okay. Next one is one more term is coming here, heat flux. One more term is heat flux, that is represented with small q. Small q. That is a ratio of rate of heat flow to the area normal to the heat transfer. That is small q is equal to capital Q divided by area. Is known as the heat flux. Q expressed in terms of watt per meter square. Q is measured in terms of watt and this area is meter square. That is Q is equal to small q is equal to Q divided by A. That is heat flux. Q is small q is equal to rate of heat flow divided by the area normal to the direction of heat flow. Normal to the direction of heat flow. That will give us the heat flux. That will give us the heat flux. Okay. Next, thermal conductivity. Next one is thermal conductivity. Thermal conductivity is the ability of a material to conduct the heat fluid. Already we defined it, K value, that is thermal conductivity. Next, the rate of heat transfer to the unit thickness of the material per unit area of the unit area per unit temperature differences. That is also defined the rate of heat transfer to a unit thickness, delta x value is 1 of a material per unit area, that is A is equal to 1 per unit temperature difference, that is T1 minus T2 is equal to 1. Okay, so in this way also we can define the thermal conductivity. The thermal conductivity of a material is the measure of ability of a material to conduct the heat. Okay. Here, a high value of thermal conductivity indicates that material is good heat conductor. So that means more value of heat is flow, more rate of heat is flowing through the substances. If it is having the higher value of thermal conductivity, higher value of K, and low value of indicates that the material is poor heat conductor or insulator. Okay, if value of K is more, then it is a more good conductivity material. If the value of K is less, then it is a poor heat conductor. Or you can say it is the insulator. Insulator is nothing but what? It will not allow the heat. It will not allow the heat flow. It will not allow the heat flow. Okay. So this is about the thermal conductivity. Okay. So next, thermal conductivity value is depends upon material structure, amorphous or crystalline. So the value of K is depends upon what? Material structure, density of the material, moisture content, pressure and temperature. So how we are going to define the value of thermal conductivity of the material? It depends upon the material structure. The structure of the material is how it builds its structure. It is amorphous or crystalline. And the density of the material, what is the density of this material? Moisture content, how much moisture content it includes, pressure and the temperature. Based on these parameters, you can get the value of thermal conductivity. It depends upon the material structure, density of the material, moisture content, and pressure and temperature. Pressure and temperature. Okay. Next term is thermal diffusivity. Thermal diffusivity. So this is the property which is very helpful in analyzing transient heat conduction problem and is normally denoted by the symbol alpha. So this thermal conductivity K value is very useful while analyzing the steady state heat transfer. Steady state heat transfer. But thermal diffusivity term is used or helpful while studying the transient heat conduction. That is nothing but the unsteady state. Transient is nothing but what? Unsteady state of heat conduction. Okay. In the steady state heat conductions, we can use the thermal conductivity value, that is K, while studying the unsteady state, while analyzing the unsteady state components, we can use the term thermal diffusivity, which is denoted by the alpha value, alpha, heat conduction divided by heat storage, that is K divided by rho Cp. Unit is meter square per second. K divided by rho Cp, heat conduction divided by heat storage, that is equal to alpha. Okay, so these are the term which is related to the conduction mode of heat transfer, where you can use the thermal conductivity value K value while analyzing the steady state heat conduction problem. While analyzing the unsteady state heat conduction problem, we can use the thermal diffusivity value, that is alpha is equal to heat conduction divided by heat storage, that is K divided by rho Cp, that is equal to meter square per second. Okay, so this table will give some values of thermal conductivity. Okay, pure metal or alloy, uh, so that copper is it is having the higher thermal conductivity 401. Okay, nickel next 91. Okay, so these are some values of thermal conductivity, values of thermal conductivity. Okay, with this we will end the today classes. If you have any doubt, you can contact.